Okay, welcome to this session. We are at the distributed parallelisms now, like this, and we hope that after this you can schedule jobs with distributed parallelism, and of course know the basic difference between threads and distributed memory in terms of memory share. And you can also explain how Julia, Matlab, or R code, depending on your choice, makes use of distributed parallelism. So we have different types of parallelisms. We were covering single-threaded and threaded parallelism in the last session. So you can use multiple cores when you have threaded parallelism, but you can only use one node. And node, as you might remember, this is basically one computer. Here, the memory is shared by all cores. And also, if we go like this, there is a library which is called OpenMP. Yes. Distributed, still you can have several cores, but you can also use several nodes, which is quite nice. Here also the memory is distributed, so that means that the different processes doesn't share any memory, but have to explicitly send information between the processes. So they can't look at the same thing unless we send some information between the processes. And here either we have language packages for R, Matlab, or Julia, or one can use the external MPI library, which could be either OpenMPI or MPICH. So the problem a little bit mentioned before is that threaded programming does not scale for more than hundreds of cores. And especially you must be within one node. So if your node is only like 16 cores, then yeah, then that is your limit. But with distributed programming, we have more scalability. So that means that we can solve bigger problems where you would need more parallel processes. So, and what I mentioned before is that there is not a common shared memory, but the individual processes, not threads, like it is in a shared memory, they have their own memory space. So if a process requires data from or should transfer data to another process, it can do that by using the send or receive command to transfer messages. So as mentioned before, if you have several nodes and want to use them in parallel, then you have to use distributed or MPI to make this happen. So for instance, in weather prediction, where you need these so-called Y jobs. But you're not limited to actually use several nodes. You can still run within a node, so you can have one process per core, like that. So a standard API, an API is the way for the program to communicate with this with the computer, basically. So a standard API is the message passing interface, MPI. And in general, that means that you have to basically rewrite your code from beginning, from scratch. So that might not be an easy task if it's a very big code. And MPI is given in external libraries, and as you are working on a HPC cluster, these are loaded as modules. And there are two common versions. So OpenMPI are available everywhere except for on Dardel, where one uses MPitch. And you could use MPitch also on the other clusters. Uh, some programs may be written in such a way that MPitch is needed. So then you have to install it maybe locally or get some help from some application expert at that center. Yes, so this we covered. Yeah, but then we also have distributed parallelization themes or scheme. I mean, the thing here is that yes, this is implemented in the code, so it's often written in the actual language, it seems. And it is a little bit different from the clean MPI because you could share some common memory, but also that you exchange information by sending and receiving messages, like for MPI. So as a summary, distributed memory, you have tasks or processes that are doing individual work. So basically, when you run it like that, if you, for instance, use 10 tasks or 10 processes, then you actually start the program 10 times. And the program is not necessarily knowing about the other ones. So they are running parallel until there are some keywords that says, okay, now we should wait for some communication and we have some send or receive. And then when this is done, we can continue the run. So we have, for instance, in weather modeling, we have many processes that run out in parallel, but then maybe for each 10 minutes, there are each 10 minutes of simulated time into the future. Then each 10 minutes, you have some communication with the other tasks, and then you can continue. Yeah. So memory is sent on demand between the tasks in small packages, and the smaller these packages are, the faster it will go as well. They cannot be too large because then we are limited by the bandwidth between the nodes or between the cores. So this is suitable for not very memory dependent tasks. I mean that each task doesn't need to have too much memory to handle. And there were two implementations. We have the native languages where we have packages or libraries that we import. These could be distributed or parallel, called distributed or parallel or similar. Then we have this external MPI. So just to remember again, cores, these are the physical units on a node. But in some clusters, for instance at Pelle in Uppsala, there might be a setting which is called hyperthreading. So that means that you can actually run 2 threads per core. and that is very typical to your home computer. You have several threads per core. So that means that you can run programs, the ordinary graphical user interface that you work a lot with, like a web browser and other things. Then you have many threads working at the same time. For clean, what do you call it, scientific software, and where you just are interested in calculations in some kind, then this hyperthreading is not a good thing. So it might be better to turn this off. So on one core you can define one thread or one task. So for instance, you cannot have several threads on one core unless you have this hyperthreading, but you can also not have one thread sharing several cores. That's not possible. Tasks, on the other hand, can have several cores, and that is called hybrid parallelisms, where you combine threading and distributed. So one case here could be that you have one node. This node is fully occupied by using 5 tasks, each having 4 threads. So within each task, we have 4 threads that are sharing the memories of 5 cores. But also we see the sum, or the multiplication here, product. 5 times 4, this is equal to 20. But we won't dig into this in this course. If you want to read more, there are some links here. And here's just an image of the robot Arnold. This should be the one. That was a robot that was controlled by MPI. So how is it used in programming languages? Like in this course. So for R, we have the distributed packages called parallel or do parallel. And one function could be for each, for instance. But also we can have MPI support by the RMPI package. For Matlab, one can use the parpool cluster. And you can have some documentation here. It doesn't support MPI more than you can read about these MEX functions. And for Julia, we have the so-called processes. I think this is built in. You don't have to install it. Then you run code with this -p, and then the number of processes you want. And by just this, you can start the REPL and using these parallelism, or you run a script with parallelisms inside. And we also have MPI that we can use. So this is the name of that package that you will need to install. So here we have some packages for R, some syntax. And for Matlab, it may look like this. So we have these syntax. And for Julia, we have these. So when you have a job, the key words here is this slurm command and tasks, or lowercase n, and then you specify how many cores you want to use. and we have the keyword srun. So then you can run a script using the different cores. You can also use -p if you want to use the built-in processes or distributed packages. Yes. If I use MPI, one can use the keyword MPI run or similar. When you are running parallel, it's good to actually make sure that you are using all the cores that you allocated. So there are ways to see how to, if you are doing this, you may have made a mistake that you allocated the several cores, but then you run the code serially. Instead, meaning that you don't have a real parallelism. So it's good to see. For HPC2N, for instance, if you go here, monitoring the use of resources, you can actually show what is happening. There may be some other clusters that have similar things. What I know as a UPPMAX user is that at least the command top should work. But then you have to log in to the node that you are running your job at. Yes. So here are the exercises. This is a parallelized code. This is 2D integration. I mean, it's parallelizable, meaning that you have to do it yourself. But sorry, this is not rendering correctly, but it's a double integral from 0 to pi over x and y of the sinus x plus y function. And this should equal to 0, but we want to actually calculate it. And these are the codes by using this built-in distributed functions. So in Julia it's called distributed. In R we use the parallel and do parallel packages. And in Matlab we use the built-in functions for using the par4 loop, for instance. Yes. So what you have to do here, if you are using, let's see, R, for instance, we want you to give the numbers. So you can set this to the number of cores you want to use. And I think this is the only thing you have to change in the code. And then we have batch scripts. Oh, it's not rendered correctly. Sorry for that. But we can look at, for instance, PDC. Here you have to change the n tasks, number of tasks. This would be equal to the number of cores that you ask for. Here we see CPUs per task. So remember, in Slurm, CPUs means basically what we would say cores. And then you run the R script like that. Yes. So try different number of cores, and you can test this. Maybe you can change that number because on your cluster there may be other number of cores per node. So you can choose something else. So, and if you are interested, you can look at MPI. It's the same same formula that is to be solved. And we can look at the differences. For instance, for Julia, we have the 4 different versions of solving the same problem, but with using different parallelisms. So we have the serial code and then the other ones here. Batch scripts are here as well. And here is an example for R using R MPI. And yes, and for Matlab, we have these challenges. So these are a bit different from each other. So with that, I'm finished. So good luck.